Let's look at the two most common reactor designs currently used around the world, both of which are water-based designs. The most common is the pressurized water reactor, or PWR. This was originally developed for use in American nuclear submarines, but now drives most of the world's nuclear reactors. So you get the actual reactor vessel, which has the somewhat enriched uranium, and water is flowing through there, carrying away the heat, and the water is pressurized so it can get to a much higher temperature. This water then flows through a heat exchanger where it generates steam. The water that's gone through the reactor never actually goes to the turbine. Instead, its heat flows through the walls of piping into a second water loop, and the second water loop, the water gets very hot, generates steam, which generates a gas turbine generator, and then sends power out to the outside world. The steam then has to be cooled down in a condenser and sent back in to be heated up again. And this condenser will often draw yet a third set of water, often from a nearby river or the sea, to keep the entire thing cool. So these reactors are normally put next to rivers or the ocean or a lake, so they have a large supply of cooling water for this third water circuit. So advantages. Water is cheap and non-toxic. And when you're exposing it to radiation, it doesn't become very radioactive itself. It can act both as a moderator and as a coolant, which is great. And these reactors are intrinsically fairly safe because let's imagine the reactor gets too hot for some reason, the water will start to boil. And when it turns into steam, its density gets less, which means it doesn't act as such a good moderator. So in fact this will reduce or stop the chain reaction very naturally. So you've got a level of safety that it makes it hard for these things to run away as a chain reaction. Disadvantage. Well, one is the water has to be kept at a very high pressure. And keeping anything at a high pressure, especially radioactive anything, is difficult. Means you have to build a very strong containment vessel with steel to hold it in at the high pressure. And actually this is a problem because the neutrons coming out from the reactor will slowly take the steel of the pressure vessel and make it more and more embrittled over time, which is ultimately sets the design life of these things. They can't last forever because the metal gets too brittle because of all the neutron bombardment. They do need enriched uranium fuel, which is expensive and difficult, and it's complex because you have 2 or possibly even 3 separate water loops. You have the water loop in the inside that's with radioactive, the steam generator one, plus the cooling cycle on the outside, and that just means there are more things to go wrong. More bits of water that have to be kept separate from each other at different temperatures and different pressures, more valves, more pumps, just more things that can go wrong. They also need to have the boric acid moderator in the water, and that can be corrosive, which again limits the lifespan of these things. You have to build them out of special anti-corrosion steel, and still over time it gets corrosive. And of course it's very hard to go into a nuclear reactor and check for the corrosion because it's so radioactive, so that's a major drawback. An alternative is the boiling water reactor, which is somewhat simpler because you only have the one main water loop. Now what happens is the water, still under high pressure but not as high pressure as before, is actually boiled in the actual reactor, and it's the steam straight from the reactor that goes and drives the turbine. This actually means that the slightly radioactive steam is going to be driving things, which means the turbine hall gets radioactive as well, which doesn't happen for a pressurized water reactor. But it makes it simpler because you've now only got one main water cycle, plus of course the cooling, rather than 2, which is just less pumps, less pipes. Also the whole thing can run at a lower pressure, which means you don't need such a strong containment vessel. It's not so hard to avoid leaks. It does however mean the whole reactor pressure vessel is larger, which makes it less suitable for things like nuclear submarines. But anyway, it's possible. So it does have the drawback that the radioactive water goes to the turbine, but the most radioactive isotope is 16 nitrogen, so the oxygen in the water has been hit by a neutron and turned into 16 nitrogen, but that only has a half-life of about 7 seconds. So in fact for these boiling water reactors, yes, it's radioactive in the turbine hall, but when it's turned off you just have to wait a few half-lives, maybe 30 seconds, before the radioactivity is pretty much all gone away. Benefit is a lower pressure, so the engineering is easier. You don't need the boric acid, so there's less corrosion, which is a major advantage. Reactors are larger, which is hard, and they still need enriched uranium. So these two, pressurized water reactors and boiling water reactors, are the most widely used in the world at the moment. There are many, many others, some of which are used, but these are the two main ones.